Tableau 6, Probabilities in Simple Settings, Part 2, Continuous Spaces. In our development of axiomatic probability, we had identified three fundamental elements which are part of the subject: the sample space, the algebra of events, and the probability measure. And the crux of the development depends upon our ability to form a probability measure, a set function, which satisfies the fundamental axioms of positivity, normalization, and additivity. We saw how in discrete settings this is possible by the simple expedient of specifying a mass function or a distribution on the integers. Now, this is all that suffices for most simple, commonplace examples, but eventually, of course, we want to move the theory to more complex settings. What if the underlying space is not discrete? How should one go about constructing a probability measure in such settings? As always, we should build up some more intuition by looking at settings where these kinds of concepts come into play. And as always, we return to the toss of a coin. So let's consider the following new experiment. Suppose one tosses a coin repeatedly without end. Now, you understand, of course, that this is a fundamentally conceptual experiment. It can never actually be performed because it demands that the coin tosses go on indefinitely. But one can conceive of doing this. This is a bona fide Gedanken experiment. Now, once you have a chance experiment like this, how should one go about putting together a probability space for this experiment? Well, let's start with de von Mises' sample space. Well, what is the sample space omega for such an experiment? Well, naturally enough, omega must consist of all infinite sequences of heads and tails. Well, okay, this is making my head hurt, but in principle, I can conceive of what that means. Right? Sequences of heads and tails, heads, 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 tails, heads, heads, tails, heads, tails, and so on, and all such sequences. It's a very large looking number of possibilities, but whatever it is, I can conceptualize it. The question now is, with this complicated looking fuzzy space, is there a simple characterization of subsets of events in such a space? And if one goes ahead and characterizes subsets of interest for us, how does one go about putting together a probability measure which is bona fide, meaning that it satisfies the three axioms? As is usual, sometimes a different perspective brings a magical clarity to an otherwise murky business. Let's try to restate the problem a little bit. But first, the identification of heads and tails is neither here nor there. You could call a head anything you liked and a tail anything you liked, and as long as there was a prior agreement, a dictionary of translation, there'd be no ambiguity in what transpires. Suppose we identify with heads or successes the number 1, and suppose we identify with tails or failures the number 0. Now, once we have numbers, our experience with mathematics through high school and through early college allows us to write down mathematical expressions for sequences of numbers. And at least formally, we can identify the sample space under consideration here as simply a sequence of digits. Inevitably, we'll call these digits letters x, and we'll use a subscript to identify the location in the sequence: x1, x2, x3, x4, ad infinitum. These x's are binary digits. They must be either zeros and ones because they represent heads and tails. All such infinite sequences of x's correspond precisely to sanitized, idealized outcomes of this chance experiment. So omega is a family of infinite binary strings. Notice all we've done is renamed heads and tails. But the moment we've renamed it, and in particular renamed it using numbers, all kinds of other memories are triggered. Perhaps we can find a different perspective for this. Let's, for example, take a look at an event of interest. So here's one. Suppose A represents the event that the first head occurs on the fourth toss. Of course, that means, and in settings like this, it is useful to build up an image of what these outcomes are in our heads before we put together a mathematical codification which compactifies and systematizes our instincts. An event A like this means that the first three tosses are tails, tail, tail, tail. The fourth toss is a head. And then following that, actually we don't care. It could be any sequence. Well, in terms of our new dictionary, writing 1 for heads and 0s for tails, this means that we're looking at sequences x1, x2, x3, x4, and so forth, where x1, x2, and x3 are 0, they represent tails, x4 is 1, it represents a head, and x5 onwards could be anything, could be 0 or 1. All such sequences, where the first three elements are 0, the fourth element is a 1, and then the remaining elements can be arbitrary, are bona fide card-carrying sample points in the event A. We have now identified very precisely what the subset of interest is. Sadly, we can't seem to make much further progress. This seems okay, this is good. We at least found a mathematical compact description for what this object is. But how does one go about constructing a probability measure in this kind of setting? This looks complex, difficult. But as always, a different perspective can sometimes open doors that were hitherto unsuspected.